This is ISODOPE's Instagram page. Nuclear energy is clean energy. Raising awareness about the need for nuclear energy. Follow for dope nerdy stuff. We got some like mirror selfies, Diablo Canyon, one uranium pellet roughly the size of a gummy bear. It's pretty. Okay, so this is like a nuclear science influencer. You can see the comment section coming. My God. Ways nuclear energy can benefit the world. This is pretty cool.
Climate change is an imminent threat to our state and our nation, our economy, and our children's future. We need to be making the transition to clean, carbon-free energy now.
Nuclear energy is essential to this strategy. It's the only way to reach our goals of 50% reduction in carbon emissions by the end of this decade, 100% clean electricity by 2035, and a net zero economy by 2050.
Now we have Miss America, who is studying nuclear power to get a degree at the University of Madison.
Now, advanced reactors, including small modular reactors and microreactors, will provide choices to communities that need a constant and reliable source of clean power.
Sunshine beaming on a good time, moonlight racing from the grave. String band playing worn out honky tonks, pretty young thing going dancing in the rain. High heel lady spitting at the knickerjack, businessman with a needle and a spoon. Coyote chewing on a cigarette, pack of young boys going at the moon. Hey darling, sleeping on the blacktop. Hey darling, running through the trees on it. Hey darling, leaving for the next town, lesson license catches up with me. Welcome to Stoughton. All of my work since I've started has been in support of sodium fast reactors. So everything to do with that technology, and it's pretty applicable. Like it's not, it started out being for like a Department of Energy test reactor, and then that got canned, like the budget got zeroed out. Now I'm working on one of the DOE's chosen demo reactors, the TerraPower Natrium reactor that's going in Wyoming.
The key thing about the Natrium reactor is the thermal energy storage system. You'd actually be using sodium to cool the reactor, so liquid metal, and that's excellent for heat transfer properties. That heat from the sodium then is ultimately put into a salt storage system. You have a hot tank and a cold tank of salt, and say you have a lot of wind, solar generation in the area, and there's a lot of electrical supply in the middle of the day. In the evening and night, when those renewables, the wind kind of tapers off in the evening, the sun obviously goes down, you're going to need more power to keep up with the supply. And so the idea there is you store this energy in a hot salt tank throughout the day, and then increase the amount of salt that's flowing to your steam generator to produce more power when you need it.
One of the big things with the current nuclear reactors and current power production is you use water. So water is readily available, it's very well known, it's very common, right? And so you can heat up water and you can spin a turbine. The problem with water is that if you want to go to higher temperatures, and you need to go to higher temperatures to get higher efficiency, if you go to higher temperatures with water, you have to go to higher pressures because you have to keep it as a liquid, not steam. So as you increase the temperature, the pressures go up. And then you run into materials problems, right? So you can typically, with materials, you can handle high pressures or you can handle high temperatures. Doing both at the same time is difficult. So typical strength of materials drops significantly as the temperature goes up. And so some of these other fluids that we're looking at, salts and sodium, you can go to very high temperatures at atmospheric pressure. So you eliminate the pressure effect and you can push the temperatures up. That increases your efficiency of the power production. It's also a little bit more energy dense too, so you can shrink the reactors down a little bit.
Okay, so this is my sodium loop. This is what we're calling like a sodium diagnostics loop, which means that it monitors the purity of the sodium, like as it travels around what would be a reactor. This is where the sodium lives when it's not running around the loop. Every time I want to run this experiment, I have to fill it, and every time I want to stop, I have to dump it back in here. This is our moving magnet pump. Instead of an impeller or something like a fan that's submersed inside the sodium that spins, and then that's where you get your flow from, we take advantage of the fact that it's a liquid metal. This program, we use something called LabVIEW, and you can customize what comes up on the screen, where all of your information comes from. And you can see it's really highly instrumented. We have a lot of thermocouples on this section, a lot of flow meters, a lot of valves. It requires a lot of attention. All of my work so far has been in monitoring and controlling the purity of the sodium. Essentially, the less pure it is, the more it eats away at the reactor components that it's flowing past. And if we want these reactors to live well into the future, it's very important that we control the purity.
I saw a place in Brazil that I was like, that's gonna be a really good spot for like a microreactor. It's like a very touristic place that's like generates a bunch of money, and it's run now by diesel generators because it's too far from the shore. Yeah. Oh.
Microreactors are awesome. If we can make that technology work, I think it will change the world.
So a microreactor is a small-scale, transportable nuclear reactor that's designed for off-grid applications such as remote communities, military bases, disaster relief.
Like replacing the diesel backup generators for a hospital or running a scientific research outpost.
The goal is to have them be transportable. So whether or not they fit in a semi-truck or they can be shipped on a boat, or even the idea of having them be able to be flown places have all been tossed around.
I'm Eric Tillman. I'm a second-year PhD student in mechanical engineering here at the University of Wisconsin-Madison. My research focuses on sodium heat pipes for microreactors.
My name is Curtis Foster. My research is on the interface heat exchanger for heat pipe microreactors. So a specific type of microreactor is the Westinghouse Da Vinci microreactor. This is a 5 megawatt electric heat pipe microreactor that uses heat pipes to transfer the heat from the core to the power cycle.
Really, any power plant use a pumped coolant loop to move heat from the reactor core to the power cycle. You have to rely on the pump to be running constantly. And for nuclear, that is a bit of a concern, because if the pump stops working for whatever reason, you're in danger of having a meltdown in your reactor core. And so the idea with the heat pipes is that they're a passive heat removal system with no moving parts. You don't have to worry about a pump breaking, or if you have to shut down the reactor for whatever reason, you don't have to worry about keeping your pumps running.
It's going to come down to economics. Is it economical to do this? Also, regulatory issues. Can you ship a nuclear reactor on a semi-truck and put it somewhere, and then can you pick that up 10 years later and ship it somewhere else to have it refurbished? These are regulatory questions that have to be dealt with.
One uranium fuel pellet is equivalent to 2,000 pounds of coal, 1 ton of coal, or 150 gallons of crude oil, right here in my fingertips.
We're at a big turning point, I think, in the industry. Seeing the first commercial sodium reactor would be amazing.
You got a fast car, I wanna take it to anywhere. Maybe we make a deal. Maybe together we can get somewhere. Any place is better.